Now we will, because now I'm muted.
Is something Angus? Hello? Testing. Yeah.
The microphone is here now.
I'm Angus, and we're talking about Islaris, which is a piece of tool we've been working on for doing formal verification of machine codes with respect to real architectural semantics. So the first question is, why do we want to do verification against machine code, right? Why not just live in some high-level language where verification is more straightforward? And there are two main reasons for this. The biggest one is, at the end of the day, machine code is what executes on your hardware. So if you do verification in some higher level language, you need to either trust, verify some compiler or compilation process. This ends up being either a significant hole in your proof or a huge verification effort. Whereas if you verify the machine code, we're done. That's what actually gets executed. The other main reason that we think about is actually there's a non-trivial amount of code we care about that's still written in assembly in code, which obviously closely related. The primary example of this that we think about is exception handlers in operating hypervisors. These get written assembly because they interact with systems features, not even about handlers. So you have to write them in assembly, and they're attractive verification targets because they form the protection boundary between user land and kernel. So they're security critical getting right quickly. So we want to do machine code verification. So what's the challenge here? Why can we not just do this super natively, standard verification, right now?
Very well.
Somebody step. So that's maybe it's Leonard. Leonard, can you mute yourself?
Maybe that'll be better. We'll see. Write down your instruction semantics, plug it into your favorite verification framework, Iris or whatever you prefer, and then you're done, right? And the problem with doing this for machine code verification is this first step, writing down the instruction semantics. If you look at the Arm specification, the Arm architecture reference manual, it's about 11,000 pages long. And I really don't want to be responsible for translating that into code. So ideally, we want to do verification of machine code with respect to some existing mechanization of the semantics. And we're in luck here, because there are existing mechanizations of the semantics for a few architectures courtesy of the Sail project. So Sail is a specialist ISA verification language. It comes with a number of models for different real-world architectures and a bunch of different backends for generating fast simulators and formal verification output. We care most about two particular models, the RISC-V model and the Armv8 model. The reason we're most interested in these is that they are complete and authoritative. So by complete, I mean they describe the entire sequential behavior of the architectures. By authoritative, I'm referring to the fact that the RISC-V Sail model is actually part of the golden model published by RISC-V Foundation. And the Armv8 model is automatically produced from the ASL specification Arm themselves produce. So we trust these specifications more than we might just simply read them ourselves. Okay, so we want to do verification with respect to the Sail semantics. The problem here is they're still enormous, right? The Armv8 model is about 125,000 lines. When you compile it to Kotlin, it gets about 2 times bigger. We've tried feeding this in doing verification directly on this before, and inevitably what happens is Tog eats all of your machine's memory and then falls over.
Not inevitably. What happens currently?
Sure, for the existing models, inevitably what happens, I think.
How big is the RISC-V?
Depends on what you mean by RISC-V. Base RISC-V is quite small, and we have them work on it in Cog, but base RISC-V is also a very small architecture that doesn't contain many instructions that you want to have. I don't know how much we've experimented with RISC-V plus enough extensions to make it sort of realistic performance architecture.
Thanks. What's the memory bottleneck?
So there are a bunch of things that we think might make life harder. The way the semantics gets compiled into Coq, it's a shallow embedding, and you start trying to unfold definitions, you end up very quickly unfolding too much of the specification, and Coq is not designed to be a super efficient programming language memory-wise. You end up if you try and like unfold this enormous term in proof modes, and
So,
it just needs to blow up.
basically objects.
Yeah. And if you manipulate them to proof is going to get even larger, it's going to refer to some objects. And we don't get far. I'm going to talk about a little bit about where this complexity comes from, because it's maybe not obvious that there should be so much complexity to models. Because you look at like some simple instruction, like this one for adding 64 to the stack pointer, and intuitively this should be simple, right? The stack pointer is stored in the register, and all this instruction does is takes that register and increments it by 64. If you look at the specification, life is a little bit worse. So the specification for the add instruction, here is a fragment of it. There's a lot more going on here than you might expect. There's a bunch of different reasons for this. So some of this is because the add instruction is co-specified with a number of other arithmetic instructions. So we see sort of parameters for dealing with other kinds of arithmetic like subtraction here. Arithmetic instructions in general can set condition flags that are used for branching. We don't care about them for this instruction, but they're still here as part of the specification. On the third line, you can see the register is being selected. That's more complicated than you might expect, because the stack pointer is not actually a single register. It's a banked family of registers that are picked depending on what mode the processor is executing in. There's not even any arithmetic on this slide. That's in another function, which does the arithmetic and also a bunch of other arithmetic we don't care about to compute the flags. And to even get to this point, I've skipped all the way past the code, which is a sort of large scale and medium complexity parser that exists inside the specification. And that's all just for a super simple instruction. And as soon as you want to touch memory, life gets a million times harder straight away. So the key observation of Islaris is that most of the time you don't care about most of this complexity. And so we separate out the sort of relevant and irrelevant aspects of the architecture for the proof that you want to do. And the objective is to prune as much of the irrelevant architecture specification as we possibly can. To do this, we use a tool called Isla, which was presented at CAF 21. Isla is a symbolic evaluator for sale. It works using an SMT solver to sort of determine which paths through the sale program are actually possible given certain constraints on the system state. And we use that to sort of produce traces that simplify away most of the specification for any given concrete instruction. That still leaves you with the sort of concrete proof on the it still leaves you with the sort of proof you want to do with the actual program that you've got given the simplified semantics. And for that we provide an Iris-based program logic, which lets you do modular reasoning using memory, modular reasoning on memory and registers, and even things like pointers. For this we provide also a bunch of semi-automatic verification with automation to deal with the tedium of some of this operation logic.
So that's a pipeline?
That is a slightly simplified pipeline, and I'm sure a slightly more detailed pipeline just a second. So how does using Islaris actually work in practice? You take the instructions of the program that you want to verify and some constraints that you believe hold at various points throughout the execution. You can simplify the instructions. You feed all of that into the Islaris front end, which is the software that we've written, that takes all of those instructions, feeds them individually into Isla. Isla uses an SMT solver to simplify them, gives you back a bunch of traces, per instruction traces. The Islaris front end then translates those traces into Coq data type. And in Coq, you can write down the specification you want to prove. Then you prove it using our program logic and ideally also mostly our automation tool thing in Coq.
So you don't have access to these simplifications once you're operating.
No, you have to sort of upfront state the things that you basically want to simplify. Obviously, in practice, you can go back and forth. What you do.
Have you considered decomposing the ISA spec on the oxide into VRAT rules?
we'd love to do more simplification, more of this in COG, so that there's less stuff living outside of the foundational sort of COG world. We run into COG performance bottlenecks super hard all the time. There are approaches that we're thinking about to make this better, but it's a lot of work on sale projects to get to better everything into a better setting inside COG.
And that would basically amount to re-implementing the Isla symbolic evaluator that heavily relies on an SMT solver inside COG.
Well, you have to do that. You also have to rewrite the current sale to COG translation to be something that we can even manipulate in COG. Okay.
So, just to recap, your program logic in COG is an inductive set of rules whose soundness proof is sort of implicitly hiding in all of the validity proved by the SMT solver on the left hand.
So the program, the way this is actually specified, there's more detail about this in the paper. We describe semantics for the Isla trace language. In COG we have program logic for the Isla trace language, which is a specified operational semantics and soundness proof we get mostly from Iris. So once your program is being compiled to the Isla trace language, you get like a perfectly good COG soundness proof. The compilation from sale to Isla traces is trusted, and if Isla it is possible to have Isla is wrong in such a way that it gives us incorrect simplification.
So in one of those boxes on the right is the specification of the semantics of the Isla trace language.
Yes.
Which box?
I guess implicitly in the Islaris logic contains
and then the Islaris program logic is proof sound in COG with respect to that operational specification of the Isla
yes
trace language.
Yes, and the Isla trace language semantics is 100 lines of COG. It's not.
And the translation of a architectural spec in sale to something in the Isla trace language is what's done on the left-hand side.
Yes. Yes, and that's completely trusted. So that's the primary weakness. And we have some mitigation for that, which I'll touch on.
It's a concept development on the right with a ground model which arrives, like we recall, in a way that is somewhat trusted, not as much as
But there is a significant, I think, positive caveat, I guess Angus will get back to. With regard to RISC-V, but not for ARM.
I'll touch on that briefly. Right, yes. So how does this how much? I kind of want to show just how much the simplification benefits us. That instruction that I showed really only a fragment of before. It was a single case. Here is the Isla trace we get for that add instruction when we specify that we're executing exception level 2, which is hypervisor mode in ARM speak. And there's a little bit of boilerplate at the start and the end, but you can see the core of what's going on here is exactly what we described in our naive semantics. Read the stack pointer register, we do some simple arithmetic, and then we write back to the stack pointer register. Perhaps more instructive than what's here is what's not here. We don't do any of the flag computation because Isla can see trivially that we don't care about it. I think it's written anywhere. We don't do any decode because we've specified a concrete opcode. So the decode is sort of all worked out by Isla for us. And we've simplified just to this single register. We no longer have to deal with this conditional choice of banks. Stack pointer registers, because we know the exception level working, and that's enough to work out what register should be used.
Do you have some kind of Isla to SMT Web 2 transfer?
This is actually the Isla trace language. The Isla trace language is heavily inspired by SMT. It has a few additional constructors.
So when you do the simplifications with SMT, must be translating Isla.
So we translate sale to SMT problems, and Isla then outputs sort of the set of possible traces in this language that we call the Isla trace language, which is how you can see looks a lot like SMT.
There's a sale doesn't.
That's sort of what I do, is turning sales traces into SMT problems.
There are, it's a bit more complicated. There is in fact a failed SMT transaction, but we're not using that here. The Isla is doing symbolic evaluation over the fail by constructing specific SMT problems, specific things, and then generating one of these traces at the end of the day.
Is the trace something that corresponds one-for-one to static instructions in the program or to the dynamic execution of the instruction?
So you get a trace per instruction. So Isla in principle can handle multiple instructions, like a whole program execution. That's not what we're doing. We take each single instruction of the program and use Isla to simplify them separately. And then for each instruction, you get actually a family of traces, not a single trace, but one of these things basically for each instruction in your program.
So you take your assembly language program, your machine language program,
Yep.
and you translate each instruction individually into a trace,
Yep.
and then you could stitch these traces all together in the order they were in the machine program to get something you could.
You can't quite stitch them together because in machine code programming, you don't have like simple flow control. You have program counter controls jumping and things. So actually, we have in COC, we have an instruction memory that contains at some subset of addresses an Isla trace that corresponds to the instruction of that address. Okay.
So you can use this to translate programs by translating each instruction individually into a trace.
Yes.
But how do you get straight line forward all the time? Why have
So a branch instruction will not be straight line. You get two traces.
what do you get?
And I'm not showing that because
The branches. If there were any internal branches within the same instructions were basic.
so if there are any internal branches that that Isla can't prove always go a particular way, very often we can give enough constraints, accurately give enough constraints that we only see one execution. Obviously, for something like a branch instruction, that's not true, right? If your branch instruction always goes the same way, you should probably just do it. And then we see two traces. Yeah. So this is how we do the simplification. We then want to do verification on top of this. And for that, we provide this program logic. It's all Iris powered, which means we get lots of high-level program logic features for free and also a soundness proof for free, which is super nice. It's in a slightly unusual form. We have these sort of 4 doubles because termination is not a particularly well-defined concept in machine code. But mostly it has the form that you'd expect. It gives a least precondition rule for every statement of the trace language. Just to give an example here, if you have a write of the value v to register r, if you initially own that register pointing to some value prime, then you can assume that register now points to the value v, and you have to continue verifying. This can still be pretty tedious, like that add instruction I just showed, which is a pretty simple example, still had 10 or 15 statements to it, most of which are trivial. So we provide proof automation powered by Lithium, which was originally part of Refined C, presented at PLPI 21, that automatically handles all of the sort of separation logic reasoning. It's almost always syntactically obvious which precondition we want to apply. It kicks out a bunch of pure side conditions that it needs to apply those weakest precondition rules and asks you to prove them later. We have a little bit of automation for that as well, at least for simple cases, but that's what you spend all of your time doing, or proving things in Islaris is proving these side conditions. It's 2 separate steps of your just to show an example, just quickly show an example of the kind of thing that we have proven using Islaris. So don't worry too much about reading the details of this code, because I'm going through it. This is an ARM example. It's the intended flow control here is that we start executing in exception level 2, which is hypervisor mode. We write to a bunch of system registers, the details of which are extremely important, but which collectively set up an exception handler. We then drop down to exception level 1, which is operating system mode. where we immediately do a hypercall back up to exception level 2 that invokes the exception handler that we've just installed. That exception handler is not very complicated. It just runs 42 to a register and then heads back to exception level 1, where we loop forever at the sort of proxy for halting. The specification that we prove here is not enormously sophisticated. It's just saying that at this sort of pseudo termination point on line 16, the register contains 42. But in order to prove this, you need to correctly understand sort of all of this flow control through multiple exception levels, and that the exception handlers are being correctly installed, and that writing to these system registers is the correct. And we can prove this pretty trivial. This proof is quite platform. If you get specification, right?
Quick question. If you actually wanted to comprehensively specify this a bit more, like what an actual application or some surrounding code would need, how much of this switching to different levels also do you need to specify, and how convenient is it to write specifications that mention these kind of additional aspects that you can go slower if you just want to specify the arithmetic pre and post condition?
I'm not sure I entirely understand the question. So if you're trying to prove correct something like a hypervisor exception handler, then you need to know sort of under what circumstances does an exception handler get executed, what happens when it gets executed, and sort of what the architecture does when you return from that exception handler. And that's all wrapped up in this sort of exception level manipulation. So most user land programs won't do all of this exception level manipulation very often, except when they go through a system. But if you want to verify your syscalls, which we do, you need to care about this stuff.
Yes, the spec of the from a user point of view, the complete spec of the hypervisor, which is providing this syscall, wouldn't be mentioning the system.
It would be implicitly mentioning them, but the joy of a program logic like Iris is that you wrap this all away in a nice invariant. It's just, you get a top level that says, when I HVC 0, I get this behavior. That will have dependence on a bunch of system state. Probably as a user, you don't care what that system state is. It can all just be wrapped up into one sort of Cocker constructor. The system state is same. And your weakest precondition for doing HVC 0 will depend on your Cocker constructor. The system state is same. As a user land program, you can hide all these details, but that's just standard program logic stuff, right? You can encapsulate a bit of code and wrap it away. So you don't have to care about the details for every proof. That makes sense.
Okay, yeah, but there needs to be a program state that captures some of that, or a predicate that captures some of the state.
Yeah, because this just isn't true if you don't know that you're operating in the same operating system environment that set up the correct syscalls for you, then you can't do syscalls and assume they're going to work.
Okay.
You tried to verify something like a user mode hello world program that makes system calls to IO through the hypervisor to your operating system call handler or IO?
Not with a realistic operating system handler, because then in order to do that in its entirety, you have to verify a meaningful fraction of Linux, whatever operating system you've got there. If you're willing to do this for a simple 20-line operating system that only supports writing hello world as a memory, I'm not sure we've done that, but that is just the concatenation of this and another example that we've done. So I don't think we have an example that does exactly that, but I also think it's just a trivial concatenation of two things that we have done.
So do you have to do that? I mean, couldn't you get, for example, a whole program encode and work with that down to the kernel?
You'd like to do it with abstraction, like
So
separately your user program.
If you're happy to assume that the kernel works, then that's something that we can do. If you want to prove that the kernel works, then for a completely trivial kernel, we can do it. For Linux, we obviously can't, but that's Linux is Linux.
No, but if you just want to do what I want to, you don't need to.
If you're happy to just assume that the syscall does the right thing, which is something that we can write down in Islaris, then yes, we can do that. I don't think we have, but it's very easy.
Or you could do you could get the whole program and you can just symbolically validate your way through the system.
When you say the whole program, do you mean the whole program, including the user mode program and the hypervisor and the deployed operating system? Yes, but surely you'd want to verify those three things separately with respect to these kind of iris
In
specs.
some context, you would, and probably want something very narrow and specific.
Okay.
Yes, we can separate. The whole point of using iris is to separate out these groups. So in case we can get specifications to have a particular function pointer works, for example, you can call it. Let me just go to directly begin so that when you time for drop to set up. So in the paper, we show a couple more case studies. The biggest one is that we do verification of another exception handler that's taken sort of as is from Google's under development PKVM hypervisor. This is significantly more code. And it's all system state interacting code. The other big example that we handle is a sort of binary search that takes a function pointer comparison function. It's not an enormously sophisticated example algorithmically, but in order to handle these function pointers in a machine code setting, we sort of handle the entire, handle the C calling convention to represent how this works. And again, Islaris, at least in this example, handles that the problems. We also give a lot more details of the formality than I have time for here. So there's a formal semantics of the Isla trace language. There's a description of the program logic and proof automation and how that works in more detail. And the thing that Peter mentioned earlier, which I can mention just very briefly, in the specific case of RISC-V, where the model is much smaller, we do translation validation between the Isla traces that we generate for an example program and the sort of sale-generated COP semantics. So in those, and we have some automation to make doing that translation validation practical. So in the specific case of RISC-V, we can actually sort of retroactively check that Isla has not introduced any inconsistencies. As of the moment, we can't do this for scale reasons. Yes, that's Lars. Thank you for listening. I just think there's many questions as 2 minutes I've got left on.
Is this translation validation something that ideally would do? Okay, let's say Puck was able to handle the get around the performance bottlenecks. Is there any advantage to doing SMT simplification plus translation validation as opposed to just doing the symbolic validation in Puck itself?
So the advantage is that
Or would there be a future advantage?
yeah, it's not immediately clear to me whether there is an advantage or whether it is.
Yeah.
It's at least possible that there's an advantage because when you're doing the translation validation in POC, you don't have to make any decisions. You just have to re-represent the decisions that the SMT solver made in COG. The SMT solver works much harder.
Yeah.
Sort of deciding which way to go. And that was, I think that did help significantly. I didn't do much of this translation validation work. The other thing is the translation validation work is just very hard and requires sort of an expert COG user. So where the SMT solver is sort of fire and forget, so you can reorder things slightly. You can make sure you can do your proof with simplified traces. And then, if you really care, do the difficult work of checking this. It's not really the same.
So, getting back at the kind of history of this, you and you did sort of going on and 68 or 28 machine code verification.
Yeah.
You and you's work from around 1919 something.
Yeah.
Then here forms of language somebody knows some verification. What they found is that as long as you were able to reverse engineer the source code, and certainly like you could actually easily almost the source code level. There was some Mechanised work also.
Yeah.
And reverse engineer the function program from the compilation program.
Yeah.
So that kind of approach would be useful, or do you really want to use something like that?
So for a very large program, which I had the C source code, but I would not want to do the proofs of that first large in the RS. What you want to do at scale is probably use C verification and then use that to inform. If you care enough, you're not willing to trust your compiler, you use that C verification to inform an Islaris proof, hopefully as automatically as possible. The big difference between Islaris and most existing work is that we're using these existing full-scale semantics, not sort of pre-simplified by hand semantics that just sort of write down these naive semantics that you believe are true actually massively underrepresent the complexity of real architectures.
So in, I don't know, approximately 2019, published a paper called Connecting Higher Order Separation Logic to a First Order Outside World, in which we proved, hello world kinds of programs correct with respect to a separation logic specification of system calls. Then we proved the implementation of the system calls correct with respect to that spec. But how you got from one place to another through context switches and the magic of the this privileged instructions was left as future work. So you've done that future work. It's actually possible to do this kind of abstracted connection.
The joy of working with the sales specifications, the pain is how big and detailed they are. The joy of working with them is that actually an HVC is not magic in Sail, right? It does some register manipulation.
Right.
And it all just becomes very, very straightforward, conceptually, at least. And so yes, that's what the problem was like. How do I justify this magic instruction goes away? It's just a register write. Or well, several register writes and some permission checks and lots of other things, but it collectively is what it's about. So I will keep answering questions until someone stops me before the going through next time, so I should.
Thanks again.
Briefly to resolve something. Well, does anyone know how I can make this not be visible? Like,
It's not clear.